This session, as you can see on the screen, is an overview of the new functions and features in z/OS V2R2. I'm going to be doing a lot of the presentation, but I'm also joined today by my colleague Gus Kasimis, who will be taking us in particular through the shared memory enhancements that are in the release. And there's a fairly significant amount of news there that you'll want to listen to. I'll also point out that on the title chart there is a link to SlideShare where we have a copy of the PDF of these charts. So if you want to download that to make notes on or just to refer to later, you can certainly do that. It's been up a while, so hopefully you grab that if you need it. With that having been said, we will move on. There's always a disclaimer chart up front when we're talking about stuff that's not actually been released yet. z/OS V2R2 is scheduled for general availability this fall. So we still are several months, almost half a year away from the GA of the product. So things could still change. A lot of what I'll talk about today has been through systems test. It's pretty much in the can, ready to go, but there are things we will talk about that are very much still under development, certainly from a test perspective. So some of this could change, just to be aware as we go through that is the case. Here's an agenda chart broken down on a theme basis. You're used to these things. We've used the same one for several releases now. We always have content on security. Simplification has been a big focus over the last couple releases. Availability is always there. So you're familiar with most of these topics. The first topic will be economics and platform efficiency. And when we talk about this particular category, we're usually talking about one of two things. Platform support, and you're going to see that when Gus starts talking about shared memory enhancements later, but also performance. And performance has been a big focus of COM server in z/OS V2R2. If there's one single theme or overarching theme across the entire release that I think of when I think about 2.2, it's scalability. As we go through this first few charts, you're going to see that we've made a big investment in extending the scalability of Communication Server. The first item in that pathway is the 64-bit enablement of the TCPIP stack and our strategic DLCs. So in general, there's been a push to get 64-bit enablement across z/OS now for some period of time, and we have always already started that and had started in previous releases. Some of that was very visible to you back in V1R13. You may remember stating that we had moved C-trace and our VTAM internal trace above the bar. Some of the things we had also done ahead of time you couldn't see because it basically was internal plumbing, but the big bulk of the work was something that had to be bitten off all at once. We had to fully enable all of the stack itself plus the primary DLCs that we communicate with the network with, things such as the OSA Express interfaces and so forth. Why are we doing this? And again, it goes all back to scalability. As we increase the workloads on the platform, as everything continues to grow, the storage demands keep increasing, and that below-the-bar storage, which has always been kind of a critical resource, it's just more critical than ever. So moving storage above the bar where possible by 64-bit enablement is a huge initiative and something that we've wanted to do for some time. We're finally now taking that step in V2R2. The next item on the scalability drumbeat relates to Enterprise Extender. The good news is that EE was already fairly scalable. We've had very few complaints from our customer base about the scalability of Enterprise Extender, so it's quite possible that there's no one on this call that will really actually need the particular enhancement I'm going to talk about here, because this one is aimed at customers that have extremely large-scale EE implementations. And when I talk about large scale, I'm talking about having 10,000 or more Enterprise Extender connections out of a single LPAR, not across your network, but a single LPAR. If you have a few thousand out of an LPAR, we've always handled that fairly well. It's when we get above that 10,000 mark that things have gotten a little more dicey. And so what's happened in 2.2 is more internal plumbing, basically some restructuring of some control blocks to remove some serialization bottlenecks and allow us to scale past the 10,000 connection mark fairly far. So again, not that interesting to many people, but there are a couple of customers worldwide that are looking to take EE into that type of territory. The next topic is about increasing the single stack dynamic VIPA limit. So the current limit on the total number of DVIPAs on the system is 1,024. This is another case where we're improving the scalability, and it may not be something that many of you, if any of you, need today, but this is more of a, we're looking down the road. We're talking about something that's going to GA in a few months, but as we go past that and you begin to roll 2.2 in production, something that you might need further down the line. With customers becoming more and more focused on cloud deployments, situations where you want to be able to dynamically deploy another application instance, and it would have its own application instance DVIPA associated with it. The current limit of 1,024 DVIPAs, not that constraining on you today, might become a constraint in the future. So in V2R2, the limit on the number of application instance dynamic VIPAs is being raised from 1,024 to 4,096. And by the way, that's 4,096 for both address families, IPv4 and IPv6. So hopefully we've given you considerable more room in that area for the future. The last scalability item I will discuss is related to our IKE daemon. Kind of like what I said about Enterprise Extender, this is not something that many of our customers have had an issue with, but some of the ones with very large IPsec implementations have seen issues, whereas they get well beyond the hundreds and well into the thousands of tunnels. And they hit a situation where they're having to negotiate the security associations for those tunnels all at once, either because of a startup or because of a failure and a restart or whatever the case may be. Sometimes the IKE daemon gets bogged down. And if you look down this chart, you'll see some of the reasons why. Clearly, one case is if the CPU is already heavily utilized on the CAC, the IKE daemon may just be not getting enough cycles to do all the things it has to do. We know that we've had particular issues with some of the older IKE v1 clients, and Windows in particularly, with how they retransmit to us, and that giving us extra workload, causing us to take longer to negotiate the security associations. So this ends up in a situation where, yes, the tunnels come up, but it may take an inordinate amount of time if we're talking about several thousand tunnels that are having to be negotiated. So in 2.2, we want to do something to improve that. So a lot of the problem relates to the fact that the IKE daemon, as we originally implemented, is mostly single-threaded. And over the years, we've done little tweaks here and there to try to improve the situation, but still everything has been largely one thread, and that can be very constraining as we get to these larger implementations. So in V2R2, we've restructured it so there's now a pool of threads that we're utilizing. And the IKE daemon is processing a lot of different types of events. It's got network events are coming in, events from the stack itself, network management interface processing is going on, timers could be popping, IPsec commands could be getting issued, and the IKE daemon has to deal with that. Whatever the case may be, there's all of these different types of work. And so now with the pool of thread, we can take these different types of work and portion them out to different threads and benefit from more parallelism. And hopefully achieve a much more scalable implementation for these multi-thousand tunnel configurations. As you'll note, it says on the chart, the impact from an externals perspective should be very minimal. There are no new knobs on this or anything else. There's more interleaved activities if you're looking at syslog. But basically, it should be fairly transparent to our users. I would love to be able to throw up a nice chart with some graphs showing you the difference between 2.1 and 2.2 processing, but at this point in time, we're not ready to release performance numbers. We're still in the middle of our performance testing, but the numbers, I will say that what we've seen is very encouraging. And it leads me to believe that by the time we GA 2.2, the scalability of our IKE daemon will be enhanced quite a bit as far as the number of tunnels we can support in a reasonable period of time. Okay, so the next chart talks about something called DelayACK processing. And many of you are probably familiar with DelayACK. Customers over the years have questions about how they set it. By default, DelayACK is turned on, but sometimes you find you need to turn it off on a global level or maybe at a port level, whatever the case may be. I mean, the idea here is that it was decided decades ago that it's very inefficient to send an acknowledgement standalone, when if you just waited for a little bit of time, you could piggyback that acknowledgement on a data packet that's going the other direction. So the idea of delaying acknowledgements to let you have something to flow that acknowledgement on. And that's not uncommon for those EE users out there. The EE's transport protocol, RTP, does the exact same thing and has since the beginning. It's a good idea, and in general it works well for our customers. There's just an issue that sometimes that you get in a situation where the sender is having to wait to send his next packet because he's not receiving an acknowledgement. And since it can be 200 millisecond delay, if nothing is coming from the receiver to piggyback the acknowledgement on, you could get in a situation, worst case scenario, where there's a 200 millisecond delay inserted between every packet flow. If it's once or twice this happens, it's not a big deal. If it's happening a lot of times across the life of a connection, then it becomes significant as far as reducing your throughput. So again, over time, people have tried to figure out how to tune this. Do they turn DelayACK off? Do they turn it off globally? Do they turn it off at the port level? How do we deal with this? Well, in V2R2, we provide a new autonomic tuning of DelayACK for you. So the default, DelayACK is still on, and you still have the option to turn it off. But there's a new option called Auto DelayACK, which allows us to monitor the acknowledgement flows on a TCP connection basis and disable DelayACK if we see we're in a situation where are these gaps occurring because of the sender side is having to wait on the receipt of the acknowledgement. If you have explicitly coded DelayACK or no DelayACK on your port or in your routing table or in a PBR policy, a policy-based routing policy, that still applies. We won't override that wins. But at a global level, you can now turn on an autonomic setting for DelayACK. Okay, this next chart is something that a few of our customers are very familiar with because it's been somewhat of a pain point for them. We shipped a function back, and I believe it was V1R11, that we call dynamic right sizing, or DRS for short. DRS was intended to help in situations where you have a long latency link. You've got a TCP connection where data is flowing across the country or across the world, or whatever the case may be, and you want to be able to send a lot of data across it, and you've got a long time waiting for acknowledgments. So the best way to achieve this is to be able to keep the pipe full by being able to send lots of packets in succession. And so DRS works by allowing the receive buffer size on the receive side to grow up to 2 megabytes. And that has worked very well for some customers. They've been very happy with what DRS has done for their performance and their throughput. One problem is that under circumstances, we will disable DRS. It's not something that had any external visibility before. It was there, it worked, it did its job. But if we saw there was a situation where the receiving application was not pulling data out of the receive buffer fast enough, we viewed that as kind of wasteful of all that storage, and so we would, in a sort of a defensive measure, disable DRS on the fly, which is all well and good. That sounds like a good idea. The problem was there was never any way to re-enable it short of re-establishing the TCP connections. And that was, obviously, it could be very disruptive in some customer environments. So this has been a pain point for several customers that had really liked the idea of what DRS could do, but on a daily basis felt like they couldn't depend on it. So V2R2 introduces the concept of DRS autonomics. And really all this does is insert a little more intelligence into the processing. It says, don't just disable DRS so quick. Let's look and see, okay, maybe the application's not pulling data out of the receive buffer all that fast, but on the other hand, we're not CSM constrained either, so why do we need to turn it off? Let's make more intelligent decisions there. But probably more importantly, if we do turn it off, let's periodically re-enable it, because whatever problem caused us to disable it might have been transient, and so we can once again take the benefit of it. So we believe that the customers that have found DRS to be beneficial in the past, this will be a very significant enhancement for them. VIPAROUTE and MTU consideration. So if we look at this chart, you see a standard Sysplex distributor configuration, and your typical customer exploiting SD in this type of situation likes to use VIPAROUTE to offload the traffic from the XCF links, and that's been a good thing, and that works great. Whenever we use VIPAROUTE, though, we have to, because we're taking the packet and rerouting it across the network to the target stack, we have to append a GRE header, a generic resource encapsulation header, which adds 24 bytes to the packet. So that could, in some cases, push you over the limit to where you now get fragmentation as the packets flow to the back end of the target stack. So that can be a bit of a performance issue. How do you fix that? Well, in the past, we've pointed out a couple things. One is that you could certainly use path MTU discovery. To do that, you're going to have to go out to all these clients, and there could be a lot of them, and enable it there. Furthermore, if this picture from the client all the way in has any firewalls, they very well may be blocking ICMP responses, and path MTU discovery certainly depends on ICMP responses, so that doesn't work very well. The lower set of bullets here talk about the fact that if you're coming in to the Sysplex distributor over standard Ethernet, but then you go jumbo frames to the back end, it's probably not a problem because you're coming in on a 1500 byte MTU and now you've got this huge MTU on the back end, so the fragmentation possibility is not going to exist. So you're good there. But we wanted to make an improvement to this, and so we have an item in 2.2 called fragmentation avoidance for VIPAROUTE, which basically says that now we're going to give you a way to adjust the maximum segment size to account for that potential GRE header that might be there. So there's a new parameter that will exist on global config called adjust VIPA MSS, which will basically reduce the size down by 24 bytes so that you never get fragmentation when we forward it from the Sysplex distributor back to the target stack. And this is kind of one of those rare cases where we're defaulting to the new and what we believe to be better behavior. The default for this new parameter will be auto, which is where we basically adjust the MSS size when we believe it needs to be. When we're talking about a dynamic VIPA on a target stack that's using VIPAROUTE or on a distributed dynamic VIPA for that matter, that's the origin. So in all those cases, we try to do the best thing. Now you can turn this off. There's a switch to turn it, or you can set this to none to turn it off. You also can force it on, where we always do this for any dynamic VIPA or packet heading for dynamic VIPA. But the default will be automatic to try to do the best thing here. Okay, the next topic is the least exciting topic in the entire presentation, and it's basically the fulfillment of a statement of direction we issued pretty much 1 year ago, where we said that there were a number of our older TCPIP device drivers that we were going to remove from support. If we just go to the next chart here, this is a table that shows all of the device drivers that TCPIP has supported for quite some period of time. It's the bottom 6 on that chart that the SOD pertain to, and it said these 6 will no longer be supported after V2R1. And so we're basically fulfilling that in 2.2 and no longer supporting activation of those device types. Now I'm going to back up and point out the bottom bullet of the statement of direction because it was very important. We were afraid we would have confusion, and we ultimately did when people saw things like CDLC. If you're an old VTAM guy, when you think about CDLC, you certainly associate that with VTAM to NCP type connectivity. SNA-Link, where it says LU6.2 and LU0 SNA-Link, a lot of people did see those and get a little bit queasy about what that might mean from a VTAM perspective and a SNA perspective. I want to emphasize that this SOD had absolutely nothing to do with any VTAM API or any VTAM device driver. This is just the TCPIP device drivers that you see listed on the table on chart 18. Those 6 have been removed from the product in V2R2. And this chart just talks about the migration of those. Hopefully this affects none of you, or at least a very, very small number of you, if at all. I think some of those are pretty much used anywhere. I think there may be still a customer or two that uses CLAW. I think there are a couple that use SNA-Link. But for all of these, there are reasonable alternative migration paths, and a lot of them are dependent on hardware devices that are long out of support. So it's really been something that you need to do anyway, was to try to move on to a more modern device type. We did ship migration health checks for this via APAR on both R13 and V2R1. Those have been available for, I don't know, 6, 8, 9 months. They've been out there a while, so if you have any question about whether or not these are activated, those health checks help you determine it. At this point, I'm going to turn this over to Gus Kasimis, and he's going to take us through our shared memory enhancements that are in V2R2.
So good morning, good afternoon, good evening, everyone. So in terms of just level setting before we jump into shared memory communications, just a brief review. So shared memory communications over RDMA, or SMC-R for short, was a key function capability that we introduced in ZOS V2R1 that basically allowed us to exploit RDMA technology, remote direct memory access technology, for TCP sockets-based applications, and do it in a transparent fashion to be able to provide 2 key benefits. For applications that are transactional in nature, have request-response type of data flows, reducing latency significantly, and then for applications that are moving larger payloads, be able to move the data faster, but also be able to reduce the CPU overhead of moving that data in and out of your ZOS systems. So in order to enable SMC-R, one of the key hardware requirements was previously running on a EC12 processor at the J2 level or a BC12 processor, and having ROCE Express cards. The ROCE Express cards is basically what provides the RDMA capability at the network layer. So ROCE, just quick, I know we have a lot of acronyms here, but quick deciphering is RDMA over Converged Ethernet. So that's basically the ability to be able to get RDMA capability on your normal Ethernet networks. So in order to play in this game, you needed basically the latest hardware, the latest adapters in ZOS V2R1 to be able to do that. You didn't need a new network, right? So this is all plugging into your Ethernet fabric. Now, in terms of describing some of the enhancements here with shared ROCE support, it's important to kind of go over what the state of the art was prior to this announcement. So as we mentioned, you needed one or more 10 gigabit ROCE Express cards on those processors. Those processors supported up to 16 physical ROCE Express features per processor. Okay. Now, in that time frame, these adapters had to be dedicated for specific LPARs. Right, so if a adapter was basically defined to LPAR 1, LPAR 2 could not use that adapter at the same time. So this is, quite different, or was quite different than perhaps your OSAs, right? Which some of you may allocate in a dedicated fashion, but others, many customers will share them across LPARs. Now, for ROCE Express and SMC-R to be exploited, one of the key things was that you needed, for high availability, you didn't want to have any single points of failure. So that typically meant that you had 2 ROCE Express features for high availability, right? So if you do the math there just briefly, right, and you had a fully populated System Z processor with 16 cards, in a high availability mode, you could support up to 8 LPARs, right, with the SMC-R capability. So that was, one of the key constraints that, I know we got a lot of early feedback from users. The other piece of this was that when you were allocating a ROCE Express card to a given LPAR, ZOS LPAR to use, that you only had the ability to use, the ROCE Express card has 2 ports. You could use one or the other ports, but you couldn't really use both of those ports concurrently. So that was another limitation that we're looking to remove. So in this time frame, and really tied to the IBM Z13 system announcement, right? So very recently we've announced our Z13 processor, and tied with that are some hardware enhancements for ROCE Express. The specific enhancement is referred to as shared ROCE support, and it is available right now exclusively on the new IBM Z13 system, right? So that is important to note that this is tied to the new processor. But what this support will do, as the name implies, is allow concurrent sharing of a ROCE Express feature by multiple virtual servers. And we say they're OS instances. So what we mean by that is multiple operating systems. And the reason we don't just say LPARs is because, in theory, this could be LPARs, right? Multiple ZOS LPARs sharing the same adapter, but it also could extend to second-level guests hosted under ZVM. So you could have virtual servers running under ZVM that also are allowed to share in this space, be able to share adapters. Now, when you look at total number of LPARs or virtual servers, we're talking about up to 31 virtual servers be able to share a single ROCE Express feature. Okay. Now, the key thing with this virtualization and sharing technology is that, ROCE and SMC-R is all about performance, and we want to be able to come up with a model that allowed us to share these adapters, yet provide minimal penalty, right, for this virtualization. So the entire design here of this is, and if you look at the picture on the right with shared ROCE, is that what we basically have there is virtual servers. You see there virtual server A, B, and C, or sharing the same physical card. And the way that we're able to do that is, as we'll see, we'll talk about physical function IDs, which we knew before PCIe function IDs, and then virtual function IDs. But the point there is that you'll see that there's a direct arrow between every virtual server and basically the card, was not taking the hypervisor out of the data path. So the idea there is that you can virtualize the adapter in a controlled manner, but when it comes to actually moving data in and out of the adapter, that there's minimal overhead that we pay for sharing that card. Right, so that's a key design point there of providing the flexibility while retaining the performance benefits of SMC-R. With this support, this will also enable us to use both ports on the ROCE Express feature, right? So both ports can be used concurrently, and in many cases, they can be shared across multiple LPARs, right? Now, the ZOS support for this. So we talked about the hardware. You need to be on the new IBM Z13 system. But in addition to that, the ZOS support that will enable this is being planned to be released both on V2R2. It will be part of the base. When you get the ZOS V2R2, that support will be inherently in TCPIP. Or if you're running today on ZOS V2R1, there will be new maintenance that's available through a PTF and APAR in the not too distant future that will enable that support on 2.1. Now, if we move to the next chart, we talked about a lot of these points, so I'm not going to hit on all of these, but the sharing support, obviously, as we said, is concurrent sharing of a ROCE Express feature across multiple logical partitions or virtual servers running under ZVM. You do have multiple PCIe function IDs. So today, if you look at how you configure the ROCE Express features to the TCPIP protocol stack, you get to specify one of these PFIDs or PCIe function IDs. Those continue to exist in this new time frame. The thing that's new there is that each one of those will now also have a unique virtual function ID that is configured through HCD in your IO-CDS process. So if you decide to share them, then you would basically, for each PCHID physical channel, you would basically have multiple PFIDs for each LPAR virtual server that wants to share it, and each one of those will have a unique virtual function ID. We mentioned the limits, up to 31 virtual servers sharing that. And basically, each ZOS instance, LPAR, or virtual server will basically consume a unique PCIe function ID. So that's no different than before. The difference here is that they could be basically now be corresponding to the same physical card, whereas previously they were all obviously required to be unique features. The capacity limits in terms of how many ROCE Express features that we support on a single processor has not changed. That's still up to 16. But with this virtualization support, right, you can think of 16 times 31, right, would be the maximum number of virtual servers that you could have access to a ROCE Express feature. The adaptive virtualization that we're providing here, other than the HCD changes that we're talking about here, the aim and the design point here was to try to make this as transparent as possible to application software, including anything that the ZOS administrator sees. But we'll see here that there are some hints on when virtualization is in play and how one determines that. So there's really very little that changes in the TCPIP configuration. Previously, when you enabled SMC-R, you had to specify the PCIe function ID and port that you wanted to use. That remains basically the rule. Virtual functions that we mentioned before that are defined through HCD are mostly transparent to COM server. You don't really need to, as a ZOS administrator, know them, specify them anywhere, but you'll see that we do provide some displays that show what those values are, which may be interesting for diagnostic purposes. So we say minor changes. Really, the only change that we have is if you're a current exploiter of SMC-R on ZOS V2R1 and you are using you have multiple TCPIP stacks configured on a single ZOS LPAR, so that's the common INET configuration, all multiple stacks in that configuration actively using SMC-R. Previously, you were able to do that by sharing the same ROCE Express feature. So you shared the same PFID across all those stacks. In this new model, that configuration will still be supported, but what we basically have is each TCPIP stack in that ZOS LPAR will need to have a unique PFID for its access. It doesn't need a unique ROCE Express card. It could still point to the same one, but it would be a unique one. So that's really a boundary case that I doubt very many customers are impacted by. Okay, so I think we talked about most things here. VLANs really don't change with this. You can have multiple VLANs, use a single PFID, so that's business as usual. You can exploit both ports, as we mentioned, but if you want to exploit both ports, you do need to allocate a new PFID for each port. So in the case where let's say a single TCPIP stack was to use both ports, you would have two PFITs potentially to the same card, each specifying a different port. Now for high availability, we wouldn't recommend that, right? We would recommend that if you're going to have multiple features, ROCE Express features, those are separate physical cards for exploitation. But you could have one LPAR use port 1 on a card, the other LPAR use port 2. That would be fully supported. And that's basically all we talked about. And there's a note there about multiple stacks is the only condition where you would really need to consider some migration actions if you're already exploiting the function in ZOS V2R1. So moving on to the next chart shows some displays. We'll look at some displays. So this first display here is the display net TRL display. And if you specify the TRLE associated with the ROCE Express adapter, what you'll see is that there is a PFIP blue line there that basically shows a PCIe firmware internal path ID for each PCHID. And what's called out there is that the first byte basically in there, that 01 that's listed in this display, is an indicator of the PCIe path that correlates to that physical ROCE Express feature. So when you look at how you plug in the ROCE Express cards into the I/O cargo cage, there's basically two distinct locations you can plug them in, and ideally each basically of those slots provides redundancy. So by being able to take, for instance, in a high availability configuration, you'd want to use a ROCE Express feature from one of the locations within the cargo cage and another card from a different location, so that there's no single points of failure in that PCI path that basically allows communication between the operating system and the card itself. So that first byte indicates whether it's basically which path is being used. So it's either path 0 or path 1. So ideally, if you had two cards, right, that you were using for a ZOS system, and you did this display for each of your ROCE Express features, you'd see one of them would have a path of 00, the other one would have a path of 01. That would ensure, again, no single points of failure, right, in terms of where the cards are located in the I/O cargo cage and the PCIe path all the way to the operating systems. Now, if virtualization is in effect, so what we told you is you didn't really change anything from a ZOS perspective necessarily, but if you're in a sharing environment, your I/O administrator may have done some changes through HCD and so forth to basically share an adapter that was previously dedicated. The way that this will manifest itself is by the red message that you see there, IST2417I. That's a new basically indicator where you'll see the virtual function that's associated with this card, right? So that basically, if you see that message, you'll see the virtual function ID that's been assigned by the HCD administrator, and just the presence of that message will tell you you're in a sharing environment. Okay? But again, so far from a ZOS administration perspective, you have not had to really specify the virtual functions anywhere. If we move to the next chart, chart 24 shows us a ZOS command. So this is the display PCIe command from a ZOS console. And you'll see there that they also will list all the various PCIe devices attached to this system. You'll see the PFIDs, and you'll see that those are all unique. Now what you'll notice is that there's a PCHID value to the right-hand side, and you'll see there that some of the PCHIDs are common now, right? So you'll see that PFID 11 and 12 are sharing the same ROCE Express card, and the way that you tell that is they have the same PCHID. And then you'll see that we said the rules are, in that sharing case, each one of those requires a unique virtual function number, and you'll see that for those two we have number 1 and number 2. So that uniqueness is only necessary within a single card. So that's why you see those values repeat for other sharing use cases where we're using different ROCE Express features. So in this picture here, we basically are dealing with 3 different cards, right, that are defined to this ZOS LPAR, right? PCHID 140, 154, and 158, but we're in a sharing mode. Okay, so that basically concludes the discussion of virtualization and shared ROCE Express support. And now we're going to go into a slightly different topic on chart 25 that discusses a topic that's come up with a lot of our users when we start discussing SMC-R. One of the key questions is, what will SMC-R provide in my environment? What benefits will it provide? So if you recall, with the support we currently have out there, SMC-R is enabled on z/OS systems, right? So this would basically, SMC-R is really about improving communications, again, reducing latency and improving CPU cost for moving large amounts of data across z/OS systems. So one of the questions is, what does that really mean in my environment, right? How much z/OS to z/OS traffic do I have? How do I determine that? So while there are methods, there's a lot of instrumentation we provide through SMF records, netstat displays, right? There's traces you could look at depending on which network management product you have, right? They could provide a lot of data that could basically help you come up with basically an answer to the question on how much traffic do I have and what type of traffic. We do find that this is a time-consuming activity, right? That requires quite a bit of expertise. So that's setting up the stage for the next chart that talks about the SMC Applicability Tool, Shared Memory Communications Applicability Tool, which is basically a tool that we're making available to help customers determine the value of SMC-R within their own environments and try to minimize the effort, right, and the impact of being able to make that decision. So this while we call it a tool, it's really integrated within the TCPIP protocol stack, and it's basically a new component that allows us to gather new statistics that you can use to project the SMC-R benefits in your environment. There's minimal system overhead for data collection and really no changes to any of the TCPIP network flows that you may have on your system. Right, so the idea would be is that this is a tool you would use on your production systems, right, to try to understand or model what potential traffic patterns, right, may be able to exploit SMC-R. It does produce reports, and we'll take a look at the types of data that's available to you for be able to quantify, some of the benefits of SMC-R in your environment. This feature will be available through the service stream on existing z/OS releases as well. So this will be a built-in feature to z/OS V2R2, but we'll also make this support available on z/OS V1R13 and also z/OS V2R1, the currently supported z/OS releases. Key thing with here is it does not require on those releases any SMC-R code to use this. You don't have to enable SMC-R, right? So even if you're running on 2.1, you don't need a ROCE Express feature. You don't need to have enabled the SMC-R feature, right? This will basically just gather data and give you some insight on whether that would be of benefit in your environment. So if we move on to chart 27, so how is this support activated? So there's a enhancement to the very TCPIP command with this new keyword called SMC-AT, the SMC Applicability Tool. And then basically you see the syntax there has a comma and a dataset name that you get to specify. So anything within the parentheses would basically be your dataset, your input dataset that has some configuration information. The configuration information is really fairly simple. You specify an interval duration, how long do you want to run this data collection and report for. And then what you get to specify is the list of IP addresses or IP subnets of your peer z/OS systems that you want to basically be able to monitor this traffic to. So these are, if you will, potential SMC-R candidate systems, right? So z/OS to z/OS patterns, we need to be able to see from a system that you turn this on, what are the peer z/OS systems that you need to communicate with. If you use a subnet, that's okay if the entire subnet is comprised of z/OS systems exclusively. If your subnets also have distributed platforms, then it's not a good idea to specify subnets, right? Because that's going to include traffic patterns potentially to distributed platforms where you don't currently have SMC-R capability. If you decide that you need to specify individual IP addresses, the key there is to specify all the IP addresses that may get used for communications with the current z/OS system. So that includes any dynamic VIPAs, static VIPAs, right, that may be used in addition to physical IP addresses. I would think in most cases, for high availability, most folks are using dynamic VIPAs and static VIPAs, but it's important to list all of those there. At the end of the interval that you specify, so you started this, you specified the IP addresses that you're interested in monitoring, and you specified an interval, let's say 30 minutes, that you want to run this during some peak workload period. At the end of that 30 minutes, a report is generated to the TCPIP job log, and in there's basically two sections of the report. One of them shows you the percentage of TCP traffic that is eligible for SMC-R. So that basically says any traffic that matches the IP addresses that you configured as remote addresses, we will basically count as being SMC-R eligible. Now the next thing it will tell you is, the second part of the report, it will tell you how much of your SMC-R eligible traffic is well suited to SMC-R. So SMC-R works transparently for all TCP type of traffic, right, across two peers that have SMC-R enabled, but it's really geared towards, longer running connections. So the idea there is it works well for request response type of workloads, and it also works very well for streaming workloads, right, that move a lot of data. The one pattern that it doesn't work out great for is if you have a very short-lived connection where a connection gets established, a very small message comes in, and a very small response goes back to the client, and then you tear down the connection, and then you repeat that entire process. In that scenario, what occurs is SMC-R needs to be able to establish an RDMA relationship across the two peers, right? So being able to perform that overhead for trivial connections, right, adds additional overhead. So even though you may speed up the data movement, the overall equation is not positive. So this is one scenario that we give you ways to be able to opt out of SMC-R, and we'll talk about other enhancements we're making. But we want to be able to exclude that type of traffic, right, from the report. So that will be provided to you. Now, if we move on to the next chart and talk a little bit about what the report looks like, and we do have a picture that goes into this in more detail, it basically consists of two sections. One of it is, the first section basically indicates which TCP traffic can use SMC-R immediately. So what that really means is it meets all the SMC-R requirements. And one of the key requirements with SMC-R, if you recall, is that the two ZOS systems that are communicating with each other need to be on the same virtual or physical LAN, right? Same Ethernet segment, right? And same virtual LAN, same subnet. So that's a key requirement that not all customer installations meet. So what we will do here is the tool will dynamically detect whether there's a direct route. So even though we have a matching IP address to a peer, do we have a direct route to that peer? If so, then we're SMC-R capable, right, eligible, and we will automatically count that in that report. The second part of the report is, well, what if you did match, right, the IP address, so you are communicating with another ZOS system, but you do not have a direct route? We will count that traffic, but produce that report in a separate section. The idea here is that this represents the opportunity, right, of potentially reconfiguring your networks to provide direct connectivity across your ZOS systems to exploit SMC-R. And we can, call out what those benefits are separately, right, so that you can basically see what that opportunity provides. So if we move on to the next chart, chart 29, this basically shows you a sample of the SMC Applicability Tool report. But basically, we're not going to go through all the details of this, but if you look at the top section, you'll see there that there's a report that talks about connections that meet the SMC-R direct connectivity requirements. So in this report, you'll see that, analysis that says 50% of your connections, of your overall TCP connections, can use SMC-R. 67% of those eligible connections are well suited to SMC-R. So that gives you a little bit more finer grain about what would be a good match towards the protocol. Then we also give you some statistics that talk about, from your overall traffic in and out of the system, how much of your traffic would benefit from SMC-R. So not all connections carry the same amount of data, so this gives you a different slice of the puzzle. Then there's some other interval statistics that we'll give you there, but the other part that I want to highlight was on the bottom of the report. Recall that I mentioned that basically for small messages that go back and forth, right, the key play with SMC-R is improving network latency. So all well-suited SMC-R traffic will notice significant, right, latency improvements, right? Our benefits that we had published previously show up to, upwards of 80% reduction in overall latency. But the other key benefit is, depending on the data size and how much data you're moving across the two peers, there could be significant CPU benefits. So what this table shows you at the bottom is, from all the applications that had traffic that was eligible for SMC-R, what was the traffic pattern? How big was the request at the API layer to send data? So we break things out to, small size, less than 1500, 4K, 8K, all the way up to sends that are greater than 256K, right? So things that will be greater than 64K could have significant, right, CPU benefits. So this is a way to show you how much of your traffic is streaming, bulk, if you will, versus transactional in nature, which is a smaller payload. What you would basically be able to do now is take this data and then try to match it up with one of our performance reports, and we'll show that later in the charts, to try to see what's the potential CPU benefit that you may see by deploying SMC-R on this system. If we move on to chart 30, there we talk about a couple of additional enhancements with SMC-R. And the first area is what we call SMC-R autonomics. So these are features to basically be able to automatically tune SMC-R and SMC-R deployment so that it is more efficient and there's less that you need to do from a user perspective. So the first one is basically automatically being able to cache SMC negative setup attempts. The idea there is, let's say you enabled SMC-R across two hosts, but there is an issue with the connectivity from an RDMA perspective where we don't really have an RDMA connectivity path across the two hosts. In that scenario, we may think we're directly connected, we may be attempting to establish RDMA relationship all the time, but failing on every connection. So the idea here is that in that scenario, let's recognize that we have frequent failures, and let's cache that information so that future TCP connections, we're not going to go over this overhead. And we'll cache these results for a certain amount of time, and then at some point in the future, time those out, right? So that if you've corrected the configuration issue, you have the ability, right, to be able to, at that point, have SMC-R really get it re-enabled automatically. The second feature we talked about was really related to there's some workload patterns or traffic patterns, specifically these very short-lived connections, right, with very small payloads that see no benefit from SMC-R. Today, we give you the ability on the port reservation statement in your TCPIP profile to turn off SMC-R for those workloads, right, on the server side, for those workloads that would not benefit from the SMC-R protocol. One of the questions we got from customers is, how do I figure out which of my servers have short-lived connections with very small payload? So the idea here is we decided to try to take that away from the administrator. So there's a new feature that basically allows us to autonomically detect that. And if we find that for a given server, we have lots of connections with very small payload that are not going to benefit from SMC-R, we'll automatically disable that. For other ones that can benefit from SMC-R, it stays automatically enabled, right? So it takes away that admin step. The next item in support here is the MTU size for ROCE. So when we announced our support in V2R1, we supported a 1K and 2K MTU size. And ROCE goes basically also supports a 4K MTU size. In this release, we'll basically allow you to be able to exploit 4K in addition to the 1 and 2K MTU sizes that you have today. And then finally, we have some miscellaneous enhancements in what we report for SMC-R connections. For instance, we will report local and remote buffer sizes that we're using internally for RDMA operations, and that's provided not only on NetStat but also on the network management interfaces that allow network management vendors to interact with us, and TCPIP SMF records. Then finally, on chart 31, this chart logically I wanted to display it a little bit earlier, but it was really related to the SMC Applicability Tool. We talked about the various data sizes, right, and that we would give you some insight on what type of data sizes are your workloads currently, right, using within your systems. This chart here shows you a chart from a performance report that shows you what the CPU benefits were that we measured, both on the client side and server side of various different payloads. What you'll see there is that if you go across the bottom, you'll see runs that have different payload sizes, starting with 1K to 2K to 4K. And one of the things that you should start seeing there is that as the message size increases, so do the CPU benefits. If you look at the rightmost one, difficult to read, but there the CPU benefits were greater than 50% reduction of CPU overhead related to networking on both the client and the server. So this could give you a means, right, of being able to start seeing what CPU benefits you may have after running the SMC Applicability Tool. Chart 32 is a very important chart. It points to our website for SMC-R, where we have pointers to comprehensive information about SMC-R, any presentations we have, performance reports, everything you can basically find in there. So the chart that we saw earlier that had the performance numbers, you'll go in there and just scan the entries that talk about performance, and you can get a lot more detail on any of these things.
So all of that was basically the first theme. If you go back to the agenda page, we talked about all the themes, but it was also the most significant investment area for V2R2. Scalability plus the SMC enhancements, most noticeably adaptive virtualization, but as you guys said, with the tool, applicability tool and other things, there was a lot of enhancements around SMC. So let's move on to another category, applications, middleware, workload enablement. And the first thing we're going to talk about under there is something called CICS transaction tracking. So transaction tracking was something that CICS introduced back in their 4.2 release. The idea was that you would have stuff coming in from web services or MQ or wherever the case might be. It comes into a terminal-only region. It bounces around from system to system. If you're trying to diagnose a problem, you wanted to be able to discover where the transaction entered from. What was the point of origin? So what was the IP address or whatever where things came in from? And so they introduced this concept of transaction tracking, which says that when the transaction came in, they would record this information associated with the transaction, and then as it propagated through the systems from task to task, it would always keep that information with it. If you look at the diagram on this page, you see if it goes from one task to the next, you always still retain that origin descriptor, which tells you where it began. And you could use the CICS Explorer tool to use that to locate tasks that have been associated with a particular transaction and maybe begin to build a picture that helps you figure out what's going wrong, if there's a performance issue, whatever the case may be. Now, we did not have any support for that until 2.2 for our CICS sockets listener, and that's something we've added now, so that now when you have a CICS transaction that comes in through our CICS sockets listener, we will associate with the transaction the origin information related to the listener, which includes the TCPIP address, the port numbers, both for the origin and the destination. It also includes the TCPIP stack name that came in under as well. So if we just go to the next chart, we can actually see a table that shows that for each transaction. This is information that gets captured at the point of origin coming into the CICS sockets listener. First of all, something that identifies that it is our listener that captured this, as well as the stack name, and again, the local and remote ports and IP addresses. We mentioned the statement of direction issued about a year ago for the legacy DLCs. Another one that was issued in that same time was about our mail function. So we have somewhat of a complicated mail story with ZOS Communications Server, in that we have three mail transports here. We have the SMTPD gateway, we have Sendmail, and we have the newer CS SMTP, which was introduced back in R11 and has been our strategic mail transport for some period of time. What this SOD issued about a year ago said was that in the future, there's no specified time frame here, but it says in the future we wanted to remove the SMTP daemon as well as Sendmail and converge our mail strategy entirely on CS SMTP. And there are some limitations pointed out on that in this SOD, especially at the bottom where it talks about there's no real replacement function there for the server capability of those two daemons, but you'll still be able to get the basic sending capability that so many of you use now from batch jobs and so forth. So as we began to go forward and talk to people about this and say how might this evolve, we talked to people about had they migrated to CS SMTP, what their plans were, and we found a lot of customers have migrated. The ones that have and maybe some that have looked at it but have not yet, both talked about a common problem, which is if I'm going to do this, how do I test it? I've got a production mail workload, and I want to be sure that if I cut over from SMTP to CS SMTP, that everything's going to work. So I'd like to be able to have a way to test that up front without actually doing the switch, which can be somewhat disruptive. So what we've introduced in 2.2 is the capability to run CS SMTP in a test mode, where it will basically take the mail and not send it, but process it all the way to the point of sending it, so that if there were any issues, we would discover those at this point. They get logged and you can analyze that. So the diagram at the bottom of the screen shows how this might work. We're going to have a little tool that will basically allow you to take a mail that's about to be queued to SMTPD and split off a copy of it headed for CS SMTP. And that way, your normal mail process continues. The mail that you tried to send goes out through SMTPD, no disruption there, everything's great. But in the meantime, CS SMTP also gets a copy. It processes it. If it hits an error, the error gets logged. And now you at your leisure can go through and look at the logs and say, well, I seem to have an issue here. Maybe this is a place where something about my mail is not working the same with CS SMTP as it did with SMTP. So this is a way to do some upfront testing rather than just a hard cutover, and prove that CS SMTP is going to be an acceptable replacement for you. It also points out on this chart that we are introducing migration health checks that will inform you that yes, you're running Sendmail, yes, you're running SMTPD, and remind you that those applications will be going away at some point in the future. Okay, another category, simplification. So simplification is certainly something many ZOS System Z customers have asked for and talked about. We have an aging workforce. We're beginning to bring in younger people. I go to the SHARE conference twice a year, and it's interesting to note that finally we're beginning to see some younger faces amongst all of us, shall we say, a bit older generation that have been associated with System Z for so long. And so when you bring in a younger crowd, how do you train them to configure the complexities of System Z? Or of course, in our case, we're just talking about Communication Server, and that alone is a lot of documentation to read, a lot to understand. So we've invested for several years now in a tool called Configuration Assistant, which runs as a plug-in to OSMF and allows you to have a graphical configuration capability for our policy-based networking functions. So if you've configured IPsec or AT-TLS or IDS or policy-based routing or any of those types of functions through Communication Server, you've most likely used Config Assistant. You can configure it via flat file, but it's very painful because there's a complex definitions, there's a lot of documentation to understand. So this tool, the Configuration Assistant, has been very helpful for our customer base in configuring these types of functions. However, that is only the policy-based functions. So what about the idea of configuring the TCPIP stack itself? As this particular chart points out, there are thousands of pages of documentation that you have to kind of understand or at least refer to when you're configuring a TCP/IP stack. And sometimes when you refer to them, maybe they're not the documentation is not particularly clear on the statement, and it's many options. So is there an easier way? So in 2.2, we are extending the Configuration Assistant to have a new perspective, which is the ability to configure the TCP/IP profile itself. We're going to provide it in a way that takes you sort of a wizard-based approach and guides you through it, or you can just go to the panels you want to configure the pieces that you know you need to. There'll be integrated health checks so that you're not configuring something in part of the CA that is incompatible with something in another part of the CA. So it allows you to kind of check your work as you go. There will be levels of configuration. You can configure at the TCP/IP stack level. You can back up and configure at the system image level where you have multiple stacks on an LPAR, or at a group level above that. Just as today, this Configuration Assistant helps you install the policy-based networking files that you create. This will help you with the actual install of the TCP/IP profile itself. Certainly, as we go forward, we need capability beyond just configuring a TCP/IP stack from scratch. We also want the ability to say, okay, now I've got a TCP/IP stack active. I want to go in and tweak a few parameters and generate the variable file that I would need to put those new parameters into effect. And lastly, the third aspect of this is, well, that's all well and good if I were deploying a new ZOS system, but I don't do that very often. What about taking an existing system out there, reading in the TCP/IP profile that exists, and then being able to modify it through the GUI? And that is something else that we're looking at doing. To be honest with you, all three of those steps I just mentioned, basic configuration, variable files, and learning an existing TCP/IP profile, will not probably be there at GA time. But this is the roadmap we're working toward. Hopefully, at least through the variable file support, we'll be there with the discovery capability to follow at a later time. So this is just a couple of charts after this to show you how this looks. And again, when I talked about on the second chart, I went through about things may change. The config assistant is something we still are very actively developing. And so certainly these panels could change a bit before you actually see them at general availability time. But this will give you a flavor for what you get. So if I've chosen to configure a TCP/IP profile, I can come into a screen here that says, okay, what type of resource do I want to configure? Do I want to configure basic security? Do I want to configure routing? In this case, I'm showing that I'm going to click on interfaces to configure those. If I do that, then I go to a screen which allows me to name my interface, maybe attach a description, choose interface type. In this case, I'm going to choose that I want to configure an OSD interface, and then the address family type. For most of us, that's going to be IPv4. When I do that, it's going to take me to a panel where now I fill in the normal type of parameters you would have on an interface definition for OSA. You've got an IP address, a prefix, maybe you're configuring a VLAN ID, maybe you're configuring a source VIPA. So all of this is in here. And for instance, I don't show it here, but that source VIPA pull down, I haven't selected one, and if I had not configured any VIPAs yet, I wouldn't be able to. That will be populated with the VIPAs that I can choose from. So there's a lot of things here that just makes it easier to go through and configure an interface as opposed to having to type it in and know all the parameters and all of that stuff. Okay, and the last thing that's in the simplification section, it's a little more of a simplification for us than you probably, and it's the elimination of another old form of coding things. This is also based on an SOD. This is an older SOD. It's 2 years old, where we said we were going to get rid of the gateway statement and converge on the begin routes block. And we really don't think this affects many customers. Most of the customers, when we go off and ask or we look at their configurations in PMRs and such, we don't see many gateway statements left. Begin routes is a much easier way, a more logical way, a way that's more consistent with other Unix-based platforms. And so again, this SOD was out there to warn you this was coming. In 2.2, the gateway statement has been removed. Okay, availability is always a hot keyword with System Z. The first thing we'll talk about under this theme for ComServer in 2.2 is the ability to activate a resolver trace without restarting the application. So the trace resolver today gives you a way to diagnose problems relating to hostname to IP address resolution. The issue, though, is there's a number of ways to enable the trace resolver. In many cases, to enable it, if it's not already enabled, you have to restart the application. And obviously, that's a very disruptive operation. It may require, you may have to schedule downtime to do that. It's not something you do during the peak of your day, so it's very inconvenient. So what we've done in 2.2 is provide the same type of information through a ctrace option. So now we can, the trace resolver information that was collected before can now be looked at via resolver ctrace records, which can be dynamically enabled and disabled. And then you also have the benefit of being able to use our IPCS ctrace tools that have been around for some time to format those traces and analyze them. So this should be an improvement for availability in any situation where you're having to debug a problem related to the trace resolver. Okay, to look at another function we introduced a while back, V1R11 introduced something called resolver caching, which was the idea that you did a resolver call that caused us to send a query to a name server. We got back an IP address from a host name or a list of IP addresses that we would cache them, and we would fulfill future resolver queries for that same host name from the cache. Prior to R11, there were quite a number of customers that would run a DNS on ZOS in what was called caching-only mode just to get this type of capability. And some of you may know that we removed our DNS in V2R1, so we no longer have that capability. One reason we could do that is because resolver caching brought to us one of the biggest benefits that people were using our onboard DNS for anyway. So this has been a valuable function, and many people have used it. But one, or at least a few customers have pointed out that there is a little bit of a weakness related to always going to DNS, in that when we do resolver caching, we're keeping the set of IP addresses we got back from the DNS in memory, and we're always using that list of addresses to satisfy future resolver calls. And typically when an application tries to resolve the host name and it gets back a list of addresses, it's just going to grab the first one. And every time a resolver call is done, we give the same list back, and if it's always the first address that's being grabbed off of that list, you're always getting the same IP address mapping to a given host name. Well, when going to DNS, you sort of got a poor man's load balancing function, because a DNS would typically round robin the types of the list of IP addresses it returned. So each time they would be in a different order, and if you pull the first one off, you got a sort of a cheap form of load balancing there. You effectively lose this with resolver caching because of the way the structure works now. So V2R2 tries to return that by introducing a new cache reorder statement in the resolver setup file that basically says that every time we have a resolver call and we fulfill it from the cache, instead of using the list as is, we round robin our way through it on a system-wide basis, so that we're trying to restore some of that non-deterministic pattern that you got by going to a DNS every time. Okay, the last thing that we're going to talk about today is security. I can't remember a comm server overview in a previous release that have a pretty good section on security, because it's always a hot topic and there's a lot of investment in it every release. The first item we're going to look at is something called TLS session reuse support for FTP and AT-TLS applications. This first chart is nothing but an overview of how FTP works. I think almost every customer on this phone probably uses EOS FTP, so I think you're very familiar with not only FTP in general, but our implementation for that matter. But just a couple of brief points to remember is that FTP uses two connections. You have a control connection that's set up initially for commands to flow between the client and the server, and then that causes the FTP daemon to spin off a server instance. Data connections are brought up then between the client and that instance to ephemeral ports, not to port 21, the port that the control comes in over, and the data flows on that data connection. So you have, as this picture illustrates, you have this pair of connections used whenever you want an FTP transfer. The next chart points out that when server authentication is used, the FTP server doesn't receive the client's certificate and can't really authenticate it. So maybe you're using TLS protection to protect that control connection that comes up first on top, and everything's good there. Now when the data connection generates, there's nothing really without seeing the client's certificate that lets us know with 100% certainty that the data connection is being established with the same partner as the other end of that control connection. So while I don't know of any documented cases of this happening in the field, it does open a bit of a possibility from the perspective of a man-in-the-middle attack, and that's what you're seeing in this picture. Well, the original RFC that talked about securing FTP with TLS is several years old, RFC 4217, and one of the things mentioned in there is that it says it's reasonable to assume that the server would insist that the data connection used a cached TLS session. So if you're securing you're already gone to the work to set up TLS, you've got a TLS session associated with the control connection. Why don't you reuse that TLS session? The benefit of this, you save a little bit from a performance perspective, but more importantly, it's already there. You know now that you're going to be talking to the same client on the data transfer as you were with the control connection itself. So this sounds like a great idea, right? And System SSL does support or has supported the ability to reuse TLS connections, but that's only across the same port pair. So in V2R2, System SSL has added the ability to do session reuse without port binding, meaning across multiple ports. That means that though the control connection is coming into port 21 and the data connection is coming into some ephemeral port, that I can reuse it anyway in this situation. And that allows me, again, to get a small benefit by not having to set up the second TLS connection, but also to be more certain that I'm actually got the two connections going to the same partner. This next chart shows the statements involved in FTP.data. There's now a secure session reuse parameter, both of the server and the client. This says, do you want to do this? Do you require that it be done? And so forth. But this is how you can turn it on and off. This is if you're using the native SSL TLS support that FTP has had for many years, but you also can control it through AT-TLS policy if you've AT-TLS enabled your FTP implementation. Now, it doesn't say, I don't have a chart that I'm showing here that explicitly describes it, but notice the title where it says TLS session reuse support for FTP and AT-TLS applications. This is also available for any AT-TLS controlling application. So if you had a homegrown AT-TLS application that you wanted the ability to reuse TLS sessions across, there are IOCTLs that allow you to specify that you want to do that. To be honest, I don't know of a use case other than FTP where this is a particularly important thing, but the capability is there with 2.2. The next chart talks about simplified access permissions to ICS cryptographic functions for IPsec. So we have a number of our customers that have explored our IPsec capabilities. Whenever we use IPsec, we depend on ICSF for a number of callable services. To be able to use those callable services, if in your ICSF options dataset you've specified checkoff yes, then the user ID has to be permitted to these various SAF resources to use those callable services. The issue is that the user ID in question here typically is not the TCPIP stacks user ID, but the application is actually sending and receiving the IPsec protected data. So what this means is if you have a lot of applications using IPsec tunnels, you had to permit a lot of user IDs to this list of ICSF related resources. So that's not necessarily complicated, but it's a long list of RACF authorizations that you had to go through. In 2.2, ICSF has helped us out with this situation by providing a new function that allows us to invoke those ICSF functions that we use under the TCPIP stacks credentials instead of the calling applications. So now instead of having number of applications times however many resources this is permits to specify, you only have to specify the number of resources, not times the number of applications. So it's a big simplification in the amount of definition involved. If you've already done that definition, you don't have to go off and change it right away. You can keep it the way it is, but in the future, if you see your use of IPsec expanding, this could be a big benefit. All right, application transparent TLS. I talked about it from an FTP perspective on the session reuse a little bit back, but AT-TLS has been around a long time, since R7, and it's been one of our most successful functions as far as customer exploitation. I would hazard a guess that 3/4 of you guys on this call use AT-TLS today, and it might even be higher than that. So it's been very successful. From our perspective, AT-TLS is wonderful, but it does put a bit of a tax on us because as System SSL evolves and System SSL introduces new things every release, we have to update our policy configuration, our configuration assistant GUI, usually netstat and NMIs and things like that, to expose those System SSL configuration capabilities through policy, through config assistant, and so forth. So that's something we have to do to keep this application transparency there. And so at the top of the chart, you see a list of things that System SSL is doing in V2R2, and a lot of this relates to certificate processing. The processing of ability to retrieve a certificate revocation list, a list of certificates that have been revoked by the certificate authority. Today, you do that generally from LDAP. With 2.2, System SSL has had the ability to retrieve those through HTTP. A big change that's come around in 2.2, support with System SSL and within COM server, is the ability to support something called Online Certificate Status Protocol, or OCSP. OCSP is a nice enhancement to certificate processing because instead of retrieving a list of certificates, a list of revoked certificates, and then working with that, it's more of a one-on-one thing. You say, here's a particular certificate I need to know about. You go to the OCSP server, it replies and says, yes, that certificate is valid, no, that certificate is revoked. So it's a simpler and more efficient way to get certificate information, and that's also being supported in 2.2. And the last security topic is one around NIST compliance. So NIST is the National Institute of Science and Technology, and this particular mandate you see in the first bullet, SPA 800-131A, was issued some time back, and it just said that by the end of the year 2013, government systems had to support a certain level of encryption, and it lists them there, TLS 11, 12, certain encryption strengths, and so forth. Well, we were in pretty good shape on this when this mandate came down. Our IPsec had long tracked to these specifications. AT-TLS was compliant with any of this stuff by the time V2R1 shipped, because that's where we included support for TLS 1.2. So we were in good shape on a broad basis, but we had a few holes, and that's just in the second bullet, the list of functions you see there, our policy agent, our Sendmail, SNMP, Digital Certificate Access Service, or DCAS. All of those were applications on ZOS Communication Server that were not fully compliant with this particular NIST standard. And so this chart then goes down through and tells you what we've done to update all of them. I don't think it's necessarily to read through all this, but the gist in all cases is that we've did whatever extensions were necessary to support TLS 1.2 in the enhanced cipher suites that this NIST standard requires. In some cases, for example, with DCAS, it was a matter of just taking an existing application, like DCAS, and AT-TLS enabling it. And then we get the benefits of all of this type of encryption support through AT-TLS. In other cases, it was made more sense for us just to do to change the existing embedded TLS support, such as you see with Sendmail, to support the new set of ciphers. Regardless, as of 2.2, all of these functions are now compliant with this NIST standard. Now, if you notice in the beginning bullet, it says there's a little more stringent time frame than 2.2. This has to be in place by the GA release at the end of 2013. So we actually did the coding for these items back very early in the 2.2 development cycle in such a way that we were able to ship these capabilities via PTF in December of 2013. We came in just under the wire, but we did make it. So these PTFs you see listed here have been available for just over a year and do provide that capability on the previous chart on V2R1. But it will also be base function as of V2R2. And with that, we come to the end of the 2.2 presentation. And there's our social media outlets, which you will continue to hear more about this as we go forward in time. We get closer to the actual availability of 2.2. The day we previewed it, all of that information went out to Facebook and on Twitter. This presentation will go off on YouTube and be linked from Facebook and Twitter. So there's a wealth of information, and there will continue to be more. Gus had spent some time going through SMC earlier. We will have another presentation coming in the next few months with even a bigger drill down into SMC-R and the enhancements in 2.2, just to give you an example of the type of stuff that you can get through our social media outlets. I know that this was a bit of a fire hose. 2.2 is a 2-year release cycle. There's a lot of information. Hopefully this gives you a flavor for what we have. We will have follow-on sessions on some of these topics later. So with that, I think we will wrap up.